Okay, gentle boys, welcome to chapter 7. We're going to be talking about fluids and pressure. All right, so really interesting topic, and I want you to take a couple minutes and consider this question. One afternoon, you go outside to find your younger sister standing by her bike with a nail in her hand. The bike has a flat tire. She wants to know why the air came out of the tire when she pulled it out. Now, don't just say, it just does, stupid. Actually, try and think about how you'd explain it to her. We're gonna, as always, I want you to come back to this question at the end of the lesson. I'll try and remember to discuss it at the end after discussing this topic. Okay, so today we're going to be discussing, as I said earlier, fluids, atmospheric pressure, and then also water pressure. So we're kind of thinking about fluids in two ways here, as air and water. So that is an interesting thing, because maybe you didn't think about fluids as both air and water. So a fluid is any material that can flow and that takes the shape of its container. So fluids include both liquids and gases. So that is sort of like a maybe not something you would came into 8th grade knowing. If you think about a gas, we know it expands so it can take the shape of its container, right? And we know a liquid will kind of flow and move into the shape of its container. So fluids can flow, both liquids and gases can flow because molecules flow easily past one another. So in both the case of liquids and gases, so we know gases sort of kind of bounce all around their container, whereas liquids, they kind of are more densely compacted, but they do flow past one another, right? So they will be able, you can pour them out of a container. And with a gas, you can open up the bottle of gas, right? And the gas will flow out, and it will flow a little bit more radically than a liquid, but it still will flow out, right? So these molecules don't really have a strong as attraction as a solid, therefore they'll flow. All fluids exert pressure. So the definition of pressure is the amount of force exerted per unit area of a surface. So if you think about area as sort of like the exposed, kind of face of something, right? Let's say this is like a can of something, right? So the area is all this space that's exposed. So there's pressure pushing down on all the areas there. So a cat must be a liquid, right? Liquids take the shape of their container while maintaining its constant volume. So cat is a liquid, right? Obviously that's a joke, but should reinforce this idea of liquids taking the shape of their container. So two things that are not in the test, I just kind of want you to know. They're not even really in your notes. You can read them over again. So the study of like how you can use mechanical properties of liquids is called hydraulics. You've probably heard of that before. And maybe you've heard of similarly how the mechanical properties of air is called pneumatics. So these two words are often used with the hydraulic pump or the pneumatic pump. So the way it kind of works is when a piston pushes down on water or gas, that pressure is going to be exerted equally throughout the whole gas or liquid, right? So therefore you can push down on this, and it'll push up with the exact same pressure up on that, which allows you to do lots of cool stuff. Like you can spread out a lot of force that way. That's the way gas brakes, that's the way brakes work. If you guys ever seen or heard like a brake fluid in your car, well, there's actually a fluid that when you push the gas pedal, the brake pedal, the brake pedal pushes down on a piston, which pushes the liquid along to tell the brake pedal, or to apply the force down on the brake pad on your car. So it goes from the pedal to the pad on the wheel through a liquid, right? So that's what the brake fluid is for. So back to kind of the idea of the bike tire. So the image below shows you the force of air particles hitting the inner surface, which creates pressure, which keeps the tire inflated, right? So if there's enough air in the bike tire, there's enough molecules of gas sort of bouncing around in there and pushing on the outer part of the tire. So when your little sister asks you, why does the air come out? Well, we can start to get this answer thinking that, well, when it's properly inflated, the air, when there's no holes in the tire, the gas stays in there. It's bouncing around the inner surface, right? And when you can put your finger down and push on the tire and it's firm, that means it's fully inflated. That means it's got a high air pressure in there, right? That means that there are more air molecules or enough air molecules in that tube to keep it inflated. So we can calculate pressure. Pressure can be calculated easily by dividing the force by the area, right? So this unit is a new unit we use for this. It's called a Pascal. So 1 Pascal is the force of 1 Newton, right? So think about a Newton, right? Pushing down. 1 Newton exerted over an area of 1 square meter. So a square meter being like an actual cube surface, 1 square meter, right? So a square meter would be the length times the width of this area, okay? So it's how much force is pushed down on this area. That's pressure, okay? So when you apply pressure, think about like when someone like applies pressure to a wound, or a masseuse applies pressure to your skin. She pushes down, right? She's pushing downward force on an area, right? So that's sort of how that works. And the unit for the Pascals is written like that, PA, like the state of Pennsylvania. So where did this name Pascal come from? Well, Pascal was a scientist, Louis Pascal, and his law, or the principle of transmission of fluid pressure, also called Pascal's principle, is a principle in which in fluid mechanics it states that a pressure exerted anywhere in a confined fluid is transmitted equally in all directions through the fluid. So same thing as I showed you before. If you apply a force going this way, right, and here's the fluid in this closed container here. This is a fluid all in here, this dark liquid. If you apply the force this direction, that the force is applied equally in all directions. So, and because we've got a lot of extra space up here, the force is going to go up, and it's going to push this piston up. So when you push over this way, it pushes up in that direction, as you can see by the F2. So F1 is the initial force, and F2 is a demonstration of how the force is applied equally. All right, so think about it like this, right? So you get a tube of toothpaste. What happens when you squeeze a tube of toothpaste at one end? Well, obviously, the toothpaste comes out the other end, right? Because you're applying force at the opposite end of the tube. That's distributing that force all throughout the tube of toothpaste, resulting in it coming out at the end. So we can calculate pressure by using this Pascal's law of force divided by area. So there's a couple examples here. Fairly easy, right? Just make sure your answers are labeled in PA when you're done. So this idea is now applied to the idea or to the concept of bubbles, right? So not just soap bubbles, but bubbles get rounder as they get bigger because fluids exert pressure evenly in all directions. So remember, a gas is a fluid too. So if a bubble, like a soap bubble, fills up with air, right, as it's blown or as it's created, it expands because the air inside the bubble applies pressure in all directions evenly. Okay, so on all those directions. Since air is a fluid, the air bubble expands in all directions. Okay. So now we can take this idea and apply it to atmospheric pressure. All right, so atmospheric pressure is the thin layer of nitrogen, oxygen, and other gases that surrounds the Earth. The atmosphere itself, the definition of the atmosphere is the thin layer of nitrogen, oxygen, and other gases that surrounds the Earth. So I'm going to show you what these 4 layers look like in a few slides. It's not actually on the next slide. So atmospheric pressure is caused by the weight of the atmosphere. So around the Earth, there's actually weight caused by these gases, right, that surround the Earth. They push down on the Earth with a certain amount of weight. So atmospheric pressure is exerted on everything on the Earth, including you. So when you walk around right now, when you're standing in your kitchen or in your driveway or wherever you are right now, there's air above you. Yes, you would agree with that. That air has a certain amount of force pushing down on you. And it's pretty cool. So you can actually calculate it. So right now, on your body, there are 10 newtons of force pushing down on you, right? So here's you on the surface of the Earth, and on every square inch of your body, there's about the weight of 10 newtons pushing down on you. So that 10 newtons is because there's air above you, right? So that's the weight on you. So if you're on a planet with less atmosphere, there's a little bit less air pressure pushing down on you. So if you maybe you can move a little more freely. So the tool that scientists and meteorologists use to measure atmospheric pressure is called a barometer. You'll learn more about that in earth science when we get into like talking about weather, because it's air pressure and atmospheric pressure is really key to determining weather, like wind patterns. Wind is created by difference in air pressure. Cold fronts, warm fronts, all that stuff is determined by air pressure. So I just wanted you to know what the name of the tool is. It's called a barometer. You've probably heard one of those before, maybe when you watch like the weather. So just a quick diagram showing you kind of how air pressure works, right? So if this is you, maybe it looks like you're in Canada here. If you're in Canada here, there's about this much air, a column of air. So this is a square meter of air pushing down on you, right? So this is why you feel the 10 newtons of force down here on the surface, right? Is because there's this much air pushing down on you, okay? And that 10 newtons is often known as 1 atmospheric pressure, right? So that can change, which I'm going to get to in a minute. And that's saying you're just at sea level, like you're at basic ground level. So I bet you can already kind of imagine how that could change as you travel around the Earth. So I told you before, I'd show you what the different layers of the atmosphere are. These are not tested on this chapter, but again, I just think you should know it. This is probably also part of earth science, but it's just good for you to know that these are the 4 main layers. There's some other smaller layers in there, but these are the 4 layers of the atmosphere, as you can see here. Troposphere, stratosphere, mesosphere, and thermosphere. So we can look at a balloon, and I know you guys love balloons based on that last lab, how much you played with them. But if you blow up a balloon, you can see sort of how this works. The air inside the balloon exerts pressure that keeps the balloon inflated against the atmospheric pressure. So as I said before, there's pressure coming down from the atmosphere on this balloon, but then there's also air in the balloon pushing back on the pressure on the outside. So that's what keeps it inflated. All right. So as long as you keep this tied up tight here, all the air is going to stay inside. And remember, we know that in a closed container, fluids exert pressure in every direction, right? So since it goes in every direction, it's going to push on all sides of the balloon and keep that balloon inflated. So how does the atmospheric pressure change throughout the world? I bet you've already figured it out. The atmosphere stretches 150 kilometers above the Earth's surface, but 80% of the gases are found within 10 kilometers. So if you think back to that diagram of the atmosphere, it's that first initial layer that contains most of the gas. So most of that gas is pushing right down on us here on Earth. Okay. So as you go to different parts of the atmosphere, the atmospheric pressure changes. So if you kind of think about it, the lower you are, there's more gas on top of you. All right, so the closer you are to the Earth's surface, the lower you are in the atmosphere, the greater the pressure is. Just think about it like stacking things on top of your head, right? If you stack more things on top of your head, the greater pressure will be on your head. So if you're on the Earth's surface, you have that all 4 layers of the atmosphere above you on pushing down on your head. But if you went higher in the atmosphere, you'd have less layers, you'd have less gas, less air pushing down on you. So the atmospheric pressure is going to be less than 10 newtons when you leave the Earth's surface, or you go higher to a higher elevation on the Earth. Okay, so let's take a look at this diagram here, kind of showing what I mean. At lower elevations, down here, at the bottom of the mountain, he's got higher pressure, right? There's just more atoms, there's more air here. So as he climbs up the mountain, he's up here, there's fewer atoms and lower air pressure pushing down on him, okay? So he's got less air sort of weighing down on his head the higher he goes. So if you travel to higher or lower points in the atmosphere, the fluids in your body have to adjust to maintain equal pressure. So if you've ever been in an airplane, or if you've ever climbed up on top of a mountain, like a really high mountain, you might have noticed that that your ears popped, right? So that is the air inside your brain, your ear canals, and your body escaping or entering your ear canals, depending on if you're going up or down. All right, so that's why. So your body, when your ears pop, you can tell your parents, "Oh, well, it's okay, Dad. The fluids in your body are just adjusting to the change in elevation." You could sound really smart, or the change in pressure. So now let's transition over to water. So we've been talking about air as a fluid. So the other major fluid is water, or water as a fluid. so it exerts pressure just like the atmosphere does. The same kind of laws apply to water. Just like atmosphere, the deeper you go, the more air pressure you'd have on you. All right, so it's kind of easier to understand this one. So if you dive down, if you've ever gone to the bottom of the deep end of the pool, you kind of feel your ears pop, you feel that ringing in your head. That's all that tons of water, or gallons and gallons of water that are pushing down on you. Because water is more dense than air, and the water exerts more pressure than air. All right, so the key kind of words here are this phrase and this phrase, right? So water is going to push down on you a lot harder than air would when it's above you. If you ever scuba dive before, you can't go a certain depth, or else honestly your skull and your brain and your ear canals will get crushed. There's just too much. There would be too much pressure on your body. So if you ever drink out of a straw, you can kind of see how a difference in pressure can increase flow. This is a key part of the lesson today. I need you guys to get this. The key thing here to know is that fluids flow from an area of high pressure to an area of low pressure. You've got to remember that. That is key for earth science as well when you start talking about meteorology. Let me show you what I mean by that. So all fluids, both gases and water, will go from an area of high pressure to an area of low pressure. If you've ever opened a pop bottle before, you hear that sound, right? Well, there's higher pressure in that bottle that's escaping to the lower pressure of the atmosphere out around it. If you've ever opened a window and had air rush out of the room or into the room, that's a change in pressure. Okay, they're all over the place. Tons of examples of it. So your lungs are a really common example. Your textbook uses this, so I'm going with it too. So when you take a breath, when you exhale, when you release air, the muscles decrease the space in your chest, right? So it decreases pressure. So the decrease in space causes the pressure in your lungs to increase. So the air in your lungs flows from an area of high pressure in your chest to low pressure outside of your body. All right, so to take it out. So when you exhale, that's essentially what's happening. And your vacuum cleaner creates an area of low pressure inside the vacuum, and so therefore the higher pressure outside the vacuum wants to rush into the vacuum, because all fluids go from area of high pressure to low pressure. Finally, the last slide is the tornado works this way. So inside the tornado, like in the funnel here, like inside that funnel right in here, is a low pressure, right? I'm writing PA, pressure. It's a low pressure there, right? So because of that low pressure, air gets sucked into it and creates this vortex, right? This spinning vortex. So the air rushes into the tornado because air goes from high to low, okay? All fluids go from high to low. Same thing as your vacuum cleaner. All right, got to remember that, guys. Don't forget quiz first thing when you come into class next time, and look back over your notes. Please shoot me a message on Schoology if you have a question or something didn't make sense or something didn't work with the video. And yeah, looking forward to that. Also, don't forget, hopefully this applies to future years, but your cartoon project's due Friday, so get that done. Thanks. Have a good night.